All
Oh,
right. Sorry for the hiccup, and
yeah.
thanks everybody for coming. So everybody in the room knows Sharon, I think, but thank you all for coming. Really appreciate it. So Sharon's been a stalwart PhD student of ours here, and he's been here since 2021. Did his undergrad at Beijing Institute of Technology, and then did a master's at UCLA. And is really had already well published and getting going, but since it's been here, had some really nice papers and some tough to get into computer vision conferences, as well as some of the medical imaging literature with more to come. So without further ado, and recently off completing a half marathon in New York 2 weeks ago, Sharon Zing. So please go ahead with their nice work on adaptable models. Go ahead, Sharon.
All right. Thanks, everyone. And thank you so much for being here. And and thanks again, Jim, for the very nice introduction. So good afternoon again. And I'm Xiaoran. And today I'll be defending my dissertation, Learning Reliable and Adaptable Models for Medical Imaging from unsupervised registration to semantic segmentation and beyond. And this work is done under the guidance of Professor James Duncan, along with my committee members, Alex Wang and Professor Lawrence State. So now we know that we're living in a world where AI seems to be able to do anything. Interacting with models such as ChatGPT or Cloud has become part of our lives. These models are called the generalist models, and they have causing a major paradigm shift in both the broader language and the vision world. The mechanism or the secret sauce that empowers these models is similar in both sides. Generative pre-training. Both maximize the likelihood of a sequence of tokens from unlabeled corpus. You don't need human annotated labels, you need a lot of data. The models learns rich, transferable representations purely by predicting the next token, whether that token is a word or a pixel. That's the recipe. And the natural question is whether we can simply apply this in medical imaging. To train such models, the scalability in data is fundamental. From past studies about compute optimal training requires data and model size to scale together, and empirically, about 20 training tokens per parameter. For a 1 billion parameter model, and 1 billion is small by today's frontier standards, you need roughly about 20 billion training tokens. At a 256 by 256 image with 16 by 16 patches, which works out to roughly around 78 million images. And remember, that's just to be compute optimal for a relatively small model. And frontier vision models are a lot larger. Natural images and language have web scale corpus that can comfortably reach this. Furthermore, the Kaplan scaling laws further describe the cause of the improvement. To reduce loss further by just 1%, following optimal conditions, you'd need roughly about 11% more data, or 20% more compute, or 14% more parameters. Even if a medical institution could afford the first 78 million images for the 1 billion model, climbing further down by reducing loss of 1% is very expensive. So here's the question I want to plant in your mind for the rest of this talk. Do we really need to grow the whole orchard if we only need an apple? In any given medical task, segment the ventricle or aligning these two cardiac frames, we don't need a model that knows everything. We need a model that does one specific thing reliably in front of one specific patient. The scaling paradigm is asking us to grow the orchard so we can pick any fruit. But is there a better way? To get to that answer, it helps to look more carefully at why the scaling paradigm works in language and natural images, because the answer tells us what we need to build instead. The scaling recipe rests on two implicit assumptions. First, clean supervision is abundant. There is effectively unlimited data, and the signal in that data is trustworthy. Second, the testing distribution is covered by the training distribution. What the model sees at deployment looks like what it saw during training, because the training set is so vast, it covers nearly everything. These are the two pillars that let you train one model once and trust it everywhere. So the question becomes, do they hold in medical imaging? Both assumptions are often violated in medical imaging, unfortunately, and it fail in ways that directly tell us what to build. First, medical imaging data are often noisy. The supervision that we have is imperfect. For example, there's no ground truth for displacement fields, expert annotations are scarce and expensive, and the signals we work with have acquisition artifacts or ambiguity. More data doesn't fix this because the data itself isn't always trustworthy. So we need models that can identify the supervision worth trusting that's reliable. Second, medical imaging data are heterogeneous. Every scanner, hospital, and modality is a different distribution. And we cannot collect enough to cover them all. So the model has to be able to adjust whatever it meets at deployment, and that's adaptable. Let me define these terms precisely, because the rest of the talk really pivots on them. By reliable, I mean the ability of a model to learn from imperfect supervision, to identify, weight, or constrain the signals that are more trustworthy. It's about getting the most out of the noisy data we have. By adaptable, I mean the ability of a model to maintain robust performance under changing data distributions, whether that adaptation happens during training by leveraging a pre-trained foundation model or at deployment when a new domain is encountered. And this is the overview of this thesis roadmap, which consists of a series of work that aim to build reliable and adaptable models. It splits naturally into two parts. Part one addresses the reliable side, identifying the reliable supervision signals for unsupervised registration. And part two addresses the adaptable side, building adaptable models for segmentation. I want to also mention the clinical anchor for the task that we chose. By having both unsupervised registration and segmentation, we aim to compute strain, which is a marker of regional cardiac dysfunction, and I'll show a pipeline in the end. Now, let's take more closely at the challenges of medical images poses. Start with what the natural image world look like. Here are some natural images, a cat, a bunny, and a dog, different scenes, different photographers, different lighting, but they have share a basic intensity distribution as they're all RGB images captured by similar consumer cameras. And a model trained on one tends to generalize to others without much trouble. This is the world that the scaling paradigm was built for. Now, contrast that with medical imaging. We have MRI, CT, ultrasound, X-ray, and even within MRI itself, T1, T2, TAC, BSSP, and so on. Each modality has different physical properties, different noise characteristics, different structural representations. A model trained on one type of data simply does not generalize to another without explicit adaptation. So the natural image assumption that all images are basically alike fundamentally doesn't hold well. And the heterogeneity isn't only across modalities, it's within them too. Even without a single modality, different hospitals use different scanners, different acquisition protocols, different contrast setting. A model trained on MRI from one institution can fail when deploying at another. So we face a fork in the road. One option is to build a single generalist model that handles everything, every modality, every scanner, every hospital. But as we have seen, that's the altar we cannot grow. The other option is the opposite extreme. Build a specialist model for every combination, every modality, hospital, scanner tuple. But the space of combinations explodes combinatorially. And every specialist still needs its own training data and validation, so neither extreme works. The generalist option is too data hungry to ever satisfy, and the specialist option is too fragmented and costly to maintain. On top of the aforementioned challenges, we also have one annotation bottleneck. Unlike natural images, where almost anyone can label a cat or a dog, medical images require highly trained radiologists to spend hours providing precise labels. This process is not only expensive, but also doesn't scale. For each new task, we need to follow the general process of collecting the data, annotating the data, and train and validate our model. If we want to adapt our models to new hospitals or new diseases, we simply cannot rely on getting thousands of new expert annotations every single time. So let me summarize the motivation in one picture. On one axis, learning scalability, how much we rely on prior knowledge to provide supervision for models. On the other, data scalability, how much annotation is available. These two extremes are both unattainable. A full generalist model needs mega-scale data. A per-task specialist needs maximal supervision. My thesis proposes somewhere in as a middle path. Identify reliable supervision by injecting some prior knowledge when labels are noisy. Build adaptable models that generalize across distribution without requiring extensive annotation. So to give you a more detail of the roadmap of today's talk, I've organized my work into these two categories. First, I'll present our work on heteroscedastic uncertainty estimation, published in McKay, which models aleatoric noise via input-dependent heteroscedastic variance. I'll then introduce adaptive correspondence scoring, published at ECCV, which is built upon the previous McKay work. Then I'll move into the second part of the talk, adaptable models, where I'll show how we can leverage large vision foundation models for ultrasound, which was also published at McKay last year. And to enable adaptation during training, I'll also present our work on energy-based models for task-naive adaptation, published at ICCV last year. So let me get started with the first pillar, identify reliable signals for unsupervised learning in the context of image registration. I know most of you guys are super familiar with the topic, but let me still briefly set it up. So image registration tries to align two images, a source and a target, by estimating the displacement field that warps one into another. The supervised version would require ground truth displacement, but that's notoriously hard to obtain in medical imaging. There's no manual labeler or for pixel-wise or voxel-wise displacement. So the practical approach is unsupervised. We minimize the reconstruction error between the warp source and the target with a regularizer like local smoothness to make the problem well posed. The data term enforces appearance similarity. The regularizers enforces geometric plausibility, simple to state. But as we will see, the standard formulation has fundamental limitations. So it helps us to view this from a probabilistic perspective. The source image is treated as a constant in this framework, the target image and the displacement as random variables. With a maximum a posterior estimation framework, the optimization decomposes to a likelihood term plus a prior. The likelihood captures appearance correspondence, and the prior captures plausibility of the displacement field. This framing makes it clear that improvements come from two flavors, making the likelihood more expressive or making the prior more plausible. And this is exactly how the three registration works map. Heteroscedastic uncertainty modeling and adaptive correspondence scoring both target a more expressive likelihood. There are different ways of modeling appearance correspondence beyond the naive assumption. And biomechanics-informed regularization targets a more plausible prior. It replaces the generic smoothness with a physically motivated strain energy prior. So all three works are answering the same question: how to make unsupervised registration trust its own supervision signal, but from two different angles. So today, I'll spend most of part one showing the efforts of having more expressive likelihood side. I'll cover heteroscedastic work as a predecessor and then dive into adaptive correspondence scoring. And then I'll touch on the biomechanics informed work at the end of part one. So let me get started with the heteroscedastic uncertainty work. So before introducing our method, I want to ground one empirical fact. Noise in medical images is heteroscedastic, meaning its variance is not uniform across the image, but depends on spatial location and on the underlying signal. It is a well-established physics property of the imaging modalities themselves, as shown on the left. The clip on the right shows this directly in cardiac ultrasound. You can see noise textures shifting across the field of the view and across time. Some regions are clean, others are speckled. But the past unsupervised registration work implicitly assumes the noise is homoscedastic. The variance is a constant across the image. Mathematically, the MSE loss corresponds to a Gaussian likelihood with constant variance, plus a smoothness prior on the displacement. This what makes the data term so straightforward. Every pixel contributes equally as noise variance sigma I is assumed to be a uniform as a constant. But from the previous slide, we know that it's not reflecting the true data distribution. Our proposal is to replace this with a heteroscedastic Gaussian, where the variance is non-uniform and input-dependent, predicted from no image itself by another network. That way, regions where noise is generally high are downweighted, and the model focuses its capacity on the regions where signal is trustworthy. This is implemented as a collaborative learning framework where we have two networks, the displacement estimator, which predicts the warp, and the variance estimator, which predicts the heteroscedastic noise variance, and they're trained together. The displacement estimator's loss weights each pixel's reconstruction error by our design SNR-based weighting, which we'll introduce in the next slide. And the variance estimator's loss makes the predicted variance consistent with the observed residuals. Naively, you'd weight each pixel by 1 over the variance. That's the standard negative likelihood. But this has a known pitfall, documented in the Beta NNL paper published in iClear 2022, where they show that gradients are dominated by low variance regions, and the model collapses. Beta NNL fixes this with an absolute reweighting. We propose a different fix, a relative reweighting based on the signal-to-noise ratio, raised to a power gamma, and we show it to be better in our experiments. When gamma equals to 0, it recovers the MSE as the weighting, as the loss. When gamma equals to 1, then it's just the full SNR-based weighting. We find gamma equals to 0.5 works best empirically, a halfway compromise that captures heteroscedastic without destabilizing the training. And here's the result. The estimated heteroscedastic variance produces an adaptive weighting map that highlights reliable regions and downweights noisy ones. And this is done in an entirely unsupervised principle and model-based way. Visually, the maps identifies an atomically meaningful structure, high weight on the coherent tissue, low weight on the noise-dominated backgrounds and edges. So far, so good. We've shown that the modeling heteroscedastic noise gives you a sensible weighting map that reflects reliable correspondence. But this map is handcrafted in a sense. It is derived from the explicit noise model. The natural next question is, can we learn an adaptive weighting directly from data without committing to a specific parametric noise model? And that question is what adaptive correspondence scoring answers. So let me introduce adaptive correspondence scoring for unsupervised registration. And the high-level idea is that instead of modeling noise explicitly and deriving a weighting from it, we directly learn a scoring map that tells us where the correspondence are reliable, and we use that scoring map to reweight the loss during training. Let's consider an MRI video capturing half of the cardiac cycle on the left. Below is the displacement field that we optimize offline between the first and last image of the video, or from the end distal to end systole frame. Stepping through the loss function, we will reconstruct the target in a systole frame from the source and distal frame and measure the reconstruction error. One may notice that even with the perfect displacement field, we still observe high errors across some regions within the image. Among many factors at play, these errors mainly arise from violations of basic assumptions, such as structural co-visibility and intensity constancy that we made in the design of the loss function. For example, in this video, the myocardium volume changes throughout the cardiac cycle as the heart contracts and relaxes. The cardiac motion introduces compressive structural visibility issue, where part of the ventricles and the myocardium that are previously visible in the end distal frame are no longer visible in the end systole frame. Additionally, spatial and temporally varying heteroscedastic non-uniform noise, as we introduced in the previous work, during image acquisition and motion ambiguities further complicate the process of establishing correspondence between points across the two frames. And the point is, these errors aren't to be optimized away. They're fundamentally irreconcilable with the loss function's assumptions. And when we minimize the loss that includes them, the gradients are noisy and misleading. To better understand how this impacts learning, let's consider the following example. On the left, we have a ground truth, anatomical labels of the source and target frames. Our goal is to warp the source image in a way that labels aligns with the target again. Highlighted in the red is the corresponding region between the two. Let's assume at epoch t, we're able to output a displacement estimate that warps the source image close to the target. But because of the acquisition noise and occlusions, the loss is non-zero, particularly in the highlighted red box, which drives the displacement estimator toward undesired local minimum in subsequent epochs. Instead of treating every pixel's reconstruction error equally, we learn to estimate a scoring map that identifies reliable supervision, a reliable correspondence. By reweighting the residuals during training, we can effectively filter out the gradients coming from noisy or occluded regions. This prevents the model from drifting away from the true underlying anatomy and leads to much more stable and accurate registration. And this is realized by another collaborative learning-like frame, where we train a correspondence estimator alongside the displacement estimator in an alternating fashion. First, we estimate the displacement field between the source and target image pair, which we warp the source using a spatial transform. Then we estimate a scoring map, which will be focused on computing the loss function, which we modify it by reweighting the reconstruction error using the corresponding scoring map as highlighted in green. When we train the scoring estimator using the estimated displacement, our key assumption is that when the images are properly registered during the training at certain epoch, the scoring map should be inversely proportional to the reconstruction residuals. Based on this idea, we designed the unsupervised scoring corresponding scoring loss shown above. However, training the corresponding scoring estimator is non-trivial. Simply minimizing this loss would lead to a trivial solution where the score collapses to 0. To ensure that we can properly learn this scoring estimator, we minimize a regularizer that biases the scores away from the trivial solution. And as these scores correspond to the surfaces that are locally smooth and connected, we additionally include a local smoothness term to prevent any irregularities in the scoring map that may introduce instabilities during training. And this final scoring estimator loss will be the weighted average of the three. We tested our method on several datasets that cover imaging modalities, including MRI, ultrasound, for registering the source and display frame to target and systole frame, which is considered a challenging task in the cardiac sequence. The third column highlights successful label propagation as measured by DICE, where the error map in the fourth column shows the residuals. Despite this being the validation set, our predictive scoring map showing the second last column can identify regions without correspondences. When used in training, it can prevent parameter drift by discounting the residuals. We also conducted an extensive quantitative analysis across 3 representative architectures, including CM-based registration, transformer-based, or diffusion model-based, and compared with some other baselines to validate our approach. In general, our approach consistently improves over baselines and produces a smooth displacement field as measured by the Jacobian determinant. Finally, to conclude, this series of work identified the limitation in the widely used unsupervised training objective due to the violation of basic assumptions in the design of the loss function. We have addressed this through adaptive corresponding scoring map that discounts irreconcilable errors during training. We note that our approach can be plugged into existing work in a plug-and-play fashion, and then the improvements come from our training strategy and incurs no extra cost during inference. Now, let me briefly cover the other side of the probabilistic framework, the prior. Up to this point, we have assumed a generic smoothness prior on a displacement field, which is fine by default, but doesn't encode any domain knowledge about what kinds of deformation the heart actually undergoes. And this is what the biomechanics-informed regularization would work. So the work is called Learning Correspondence of Cardiac Motion from Images using biomechanics-informed modeling. And the motivation is that the heart isn't an arbitrarily deformable object. It has no mechanical properties. We should be using the knowledge as a prior instead of the generic smoothness. So the method replaces a standard smoothness regularizer with a strain energy density prior. Concretely, we treat the predicted displacement as a deformation field on a continuum, compute the strain tensor, and penalize displacement whose associated strain energy is implausible high at a standard hyperelastic model of cardiac tissue. This biases the model toward displacement that are not just smooth, but physically plausible for the cardiac motion specifically. The result is more anatomically faithful displacement field, with a quantitatively better smoothness properties, measured by the Jacobian determinant. And improved accuracy on cardiac registration benchmarks. This work was an early proof of concept that domain priors can substantially improve the registration, supervised registration. So let me summarize the part 1. The goal was to develop reliable supervision for unsupervised registration. The probabilistic framework gave us 2 levers: a more expressive likelihood addressed by the heterozygotic uncertainty and adaptive correspondence scoring, and a more plausible prior addressed by the biomechanics-informed work. Together, they make the unsupervised registration objective robust to the kinds of noise ambiguity that pervade in real-world medical imaging data. Now, transition to part 2, building adaptable models for segmentation. Similar overreaching goal, but a different task and a different kind of challenge. In part 1, we're mostly dealing with imperfect supervision. In part 2, we're dealing with the distribution shift. And the first piece of the work I'll cover is training time adaptation, specifically adapting a large vision foundation models for ultrasound segmentation. And this project, again, is called Adapting Vision Foundation Models for Real-Time Ultrasound Image Segmentation, and was conducted when I was doing my internship at United Imaging Intelligence back in 2024. The setting is that we want to leverage the power of modern vision foundation models, which have absorbed enormous amounts of natural image knowledge, and adapt them efficiently to a specialized medical domain. In the context of segmentation, the SAM series has demonstrated remarkable capabilities in zero-shot and few-shot segmentation across a wide range of natural images. SAM in 2023 has groundbreaking for segmenting anything on static images. SAM2 in 2024 extended the capability of images and videos, and most recently, SAM3 in the last year has moved to segment anything with concepts, further pushing the boundaries of what these generalist models can do. However, apply these models naively to medical imaging data would not work, and thus specialized modules need to be designed to bridge this gap. Before introducing the adaptation scheme, it is helpful to briefly review the architecture of SAM2. In particular, the image encoder in SAM2 is HERA, a hierarchical vision transformer that captures visual features and multiple spatial scales. The hierarchical design allows the model to represent both fine-grained details of higher-level semantic structures, which is important for segmentation tasks. On the other hand, adapters are small trainable modules, typically implemented as lightweight linear layers with activation function that improves model flexibility without requiring the entire foundation model to be retrained. Prior work has explored different placements for adapters within a transformer layer, as shown in above, including pre, post, parallel, intermediate configurations. Empirical studies have shown that placing the adapter after the feed-forward layer generally yields the overall better performance. And built on these ideas, we propose our parameter-efficient adaptation framework. We take the HERA backbone from SAM2 and insert adapters for efficient tuning. Our key contribution is to utilize multi-scale features and integrates features from another powerful foundation model, DynaV2. While SAM is great at finding boundaries, DynaV2 excels at learning rich semantic representations. By interleaving these DynaV2 features with the HERA features, we provide the model with a much richer and more robust understanding of the scene, which is crucial for segmenting the often indistinct boundaries in ultrasound images. We introduced this lightweight adapter placed after the skip connection in the HERA's multi-scale attention block. Each adapter consists of a down projection layer, followed by GALU activation and an up projection layer. During training, only the adapter parameters are updated, enabling efficient fine-tuning of the foundation model. To decode the multi-scale features, we propose a hierarchical decoder that progressively fuse the cores to find representation. At each scale, it upsamples the core's feature map via transpose convolution, integrates finer scale features through concatenation, and refines them with a convolutional block. This ensures effective spatial propagation while preserving multi-scale context. The results of this approach are quite striking. On the cardiac ultrasound data, our method remained highly effective, even when trained with 1% of the original training data. And that translates only 12 examples on the canvas, but tested on the full 400 examples, significantly outperforming the baselines. And this demonstrates extreme data efficiency. Furthermore, the model shows strong cross-dataset generalization on thyroid ultrasound, and we achieved state-of-the-art segmentation result on TN3Ka and DDTI when the work was submitted and accepted. We also validated its real-world applicability on some in-house dataset where the model correctly handled cases where the thyroid gland was absent. To understand the model, what the model is seeing, we visualize the DynaV2 features using the principal component analysis. Even before any segmentation had, the DynaV2 features already capture meaningful anatomical semantics, different tissue types, structural boundaries, contextual regions. This helps explain why the model performs so well to indistinct ultrasound boundaries. The semantic pry from DynaV2 carries most of the load. This method also runs pretty fast during inference, and it achieves roughly about like 30 frames per second on an L40S GPU, and up to 77 frames per second on Tensor IT and on Tensor RT. making it plausible for real-time feedback during the clinical ultrasound exam. And in summary, we've demonstrated a method for adapting large vision foundation models to the challenging domain of ultrasound segmentation. By combining parameter-efficient adapters with multi-scale feature integration, our method achieves state-of-the-art generalization, shows remarkable data efficiency, and maintains real-time performance. This provides a clear pathway for leveraging the power of foundation models in specialized medical domains where annotated data is scarce. So zooming out again. Part 2's first contribution gives us the training time adaptation via foundation models. But there's another regime where adaptation matters even more, at deployment. Because no matter how well we adapt during training, we can anticipate every distribution a model will encounter in the wild. So we will also need to be able to adapt during inference itself, on the fly, without any labels for the new domain. And that's where the second piece of part 2 comes in. Test time energy adaptation for segmentation. This is a fundamentally different kind of adaptation. It happens after deployment on each individual test image with no access to source data or label. The work itself is called progressive test time adaptation, energy adaptation for medical image segmentation. And the core idea is to train an region-based energy model on the source domain that knows what good segmentations look like. And at test time, use it to detect and correct out-of-distribution predictions. Let me set up the problem. In real clinical deployment, segmentation models face covariance shift. Heteroscedastic noise, inconsistent imaging protocols, scanner variability. And these shifts degrade segmentation fidelity. The clean solution would be to retrain on a new domain, but that requires access to a curated target dataset, which is quite impractical in many clinical settings. Test time adaptation, or TTA, is the alternative. Calibrate the model on the fly during inference without ever needing a separate adaptation dataset. To be precise, test time adaptation is the task of adapting a pre-trained source model to the target domain. Critically, this must be done in an unsupervised manner, meaning without access to the source data or any ground truth labels for the test image itself. You take a source pre-trained model, process a single target image through a single unsupervised update step, and then you get an updated model calibrated to that specific image. To make this work without labels, we need some signals that tells us when the model is wrong. Our signal is the region-based energy model. So these models naturally capture distribution and alignment. They assign low energy to samples that fit the training distribution and high energy to samples that don't. We propose a region-level shape energy model trained on source domain segmentations. It assigns low energy to anatomically plausible shapes and high energy to implausible ones. So when the segmentations models produces OOD prediction at test time, the energy model flags it. High energy regions are exactly the regions we want to correct. Training the energy models requires positive examples, accurate segmentations, and negative examples, the bad ones that we think we would encounter during test time. Positive examples are easy. They're the source domain ground truths. But how do we get, or where do we get the bad segmentations for training? Real world bad segmentations are hard to come in any structured way. And our solution is that we curate them by using the adversarial training, by probing the segmentation model with inputs optimized to produce OOD-looking outputs. This explores the space of plausible but wrong shapes that the model can produce and gives the energy model the negative examples it needs to learn a robust decision boundary. At test time, here's the loop. We have the pre-trained segmentation model and the pre-trained energy model. The segmentation network produces an initial prediction. The energy model evaluates it, assigning high energy to likely erroneous regions. We then update the segmentation network parameters to lower the energy of its output. We iterate step by step. The prediction is pulled toward the low energy manifold of the plausible shapes. The adaptation is unsupervised. We never see ground truth, but the energy model serves as a learned region-aware critic. Here it looks like in practice. The initial predictions has a clear erroneous boundary, and the energy maps highlight the region as high energy. As we adapt progressively, the prediction is refined to a much smoother and atomically plausible segmentation. The key here is to be progressive, a small energy-guided updates that cover that converge to a robust result rather than a drastic overcorrection. Quantitatively, the method is can be plug and play across different segmentation architectures and consistently outperform baselines across 8 medical data sets from our experiments. So this isn't to be tuned to be a single setup. It's relatively a general TTA framework that works across architecture and tasks, which is exactly what you want from an adaptation strategy. And to wrap this part of the work, we propose an energy-based formulation for test time adaptation in medical segmentation. We use adversarial perturbations to explore energy landscape and enforce shape priors. The shape energy models exhibit strong OOD detection, over 92% accuracy in identifying erroneous segmentation regions. And the framework achieves state-of-the-art results across diverse medical data sets. And to flag this through one more time, the energy map here plays the same conceptual role as the scoring map in adaptive correspondence scoring, a learned special signal that tells us where the model is failing and drives the correction there. So that completes the technical contributions. Let me restate what we have. Part 1, reliable supervision via expressive likelihood, heteroscedastic uncertainty, and adaptive correspondence scoring. The plausible prior, biomechanics informed radicalization. And in the part 2 of the talk, we talked about a bunch of adaptable models, either through training time adaptation from foundation models and test time adaptation. So the ideas in this thesis turn out to be extend beyond medical imaging. The same test time and energy adaptation framework also works for monocular sparse depth completion. And during my, similarly, following the similar concept, during my Amazon internship, we also proposed a cycle-consistent re-ranking mechanism at test time, which we showed to address a fundamental limitation in semantic correspondence, improving its matching performance. So the reliable and adaptable framing isn't medical imaging specific. It can be a general lens for working with limited or imperfect supervision in the general vision world. And I'm happy to discuss either of these in a more in-depth in the question and answer section. So now let me bring everything back to the clinical anchor I mentioned at the start, cardiac strand analysis. Traditionally, strand analysis requires labor-intensive annotation of cardiac geometry, segmenting the myocardium frame by frame, tracking manually. And with our methods, that pipeline becomes feasible to be end-to-end. Unsupervised displacement estimation from registration methods that we developed in part 1, plus adaptive segmentation in part 2, give us a scalable label light 3D cardiac analysis. We apply our method to cardiac strand analysis where we tested on a clinical 3D echocardiography sequence from a patient. And after estimating the displacement field from end-diastole to end-systole frame, we compute green Lagrangian strain at each voxel. We were able to use the derived strain to identify regions of myocardial infarction as confirmed by the patient's clinical record, which indicated akinetic septal and inferior walls. This suggests the potential of our approach in improving diagnostic quality for cardiac conditions. And looking forward, there are still some works that need to be done. First, extending evaluation more systematically to 3D and a broader set of modalities. Current results are mostly focused on 2D public datasets. Second, expanding clinical validation, particularly calibrating regional strain values against ground truth simulated measurements, and improving robustness across patient populations. And thirdly, this is something we have been doing, I think, incorporating physics-based constraints and material properties more deeply. So the registration priors reflect not just being generic smoothness, but more realistic cardiac biomechanics. And that part concludes the technical part of the talk. And I want to use a dedicated acknowledge section to wrap things up a little bit. So this is the fun part, getting through the PhD. It's a journey full of scientific adventures. It's very exciting, but it's always the people that we meet along the way who make the journey memorable. So therefore, I want to dedicate this section to those who have supported, inspired, and accompanied me throughout this journey. So where the journey begins, I took a screenshot of the email Jim sent me roughly more than 5 years ago, where I'm beyond excitement to see that. So I was walking down the Levering Avenue from my apartment, I think it's called Strathmore at Regency, all the way to the In-N-Out Burger to get roughly my late lunch. And I saw the email, it was 3:12, I think, and I'm so excited. So again, thanks very much, Jim, for the opportunity. And it was also such a coincidence that both Jim, Alex, and me went to UCLA before. And next to my committee members. First to Jim, thank you again for the opportunity of being here and for trusting me with the freedom to explore. So thank you for being the big captain of this boat, leading us to sail through both calm waters and rough waves. The wonderful culture here at IPAC owes so much to your leadership, generosity, and vision. And next to Larry, thank you for being so patient and for listening all the ups and downs along the way, especially for the encouragement you gave me during the hard times. So thank you for being so approachable, and it really means the world to me. And finally, to Alex. So anyone who worked with Alex would agree that he's a truly outstanding academic, one of the most hardworking, passionate, and inspiring people I've ever met. So working with Alex has been very transformative for me. And thank you for introducing me to the world of vision, shaping my research, crafting my research skills, and encouraging me to stay strong under pressure and throughout the challenges.
You need a photo. Oh, you got it.
Yeah, and then to our great iPad community. So to Nietzsche, to John, to Xenios, who just left, and Herman, who's not here, and also to Melina, our great administrative assistant, who have been helping us so much throughout the journey. And so thanks first to Nietzsche and John. Thank you for being so kind and nice to our students. And thank you so much for organizing so much fun activities like March Madness, Bracket, Bonfire Party, and DLRG. And I missed so many friends along the way. I'm trying to name everyone in the world, but Ziqi, Anne, Junling, Camille, Jiayang, Tian, and Horace, Sean, Andrew, Ray, and Jenny. I'll put in the next slide. So, and also Illinois, Tall. Thank you. And also to our friends who are not here, Kevin, Sean, Daniel, Suyan, and especially Daniel and Suyan, who have been helping me so much with my job search. Yeah, and especially Andrew, thanks for finishing the half marathon with me, and it's a fun journey. So next to my great collaborators, Yale Vision Lab and White Trick. So thanks Jenny for coming here, being the representative. And working with you guys has been really fun. And thanks for the our White Trick folks for giving us the great data. And I did 2 industrial internships, one at United Imaging, so I also want to acknowledge them. Like both internships turns out to be great, that we have works published or currently under review. And it has been really fun throughout the 2 memorable summers, one in Boston and the other in Seattle. And finally, to my friends and family, I'm not sure, some of them may be here on Zoom, Chen Yang, who have been knowing since I was 14, 13. And also Camille and her husband, Ruochen, Jiayang, Jiao, Suyuan, and Daniel again, for all the happy weekends that we spent together. And also finally to my family, who haven't seen for a while, but hopefully I will, very soon. And finally to my wife, Xintong, who has been the sponsor of the snacks and the drinks. So yeah, if you met her, say thanks to her. And thank you for being my biggest supporter and a cheerleader, my best training partner, my best chef, and most importantly, my best friend. And thank you for sharing all the tears and joys together. And I cannot wait to share with you more in the future. Yeah, so maybe you guys already forgot what I said about the technical part, but I still want to kind of convey the last takeaway message. So when you, in the field, we know that people are kind of moving toward all the generalist model. They're trying to unify everything. But in our medical imaging scenario, when you only need an apple, just grow an apple tree instead of the whole orchard. And that concludes my talk today. And thank you again for the time being here, and happy to take any questions.
Sharon, thank you for inspirational ending and interesting talks. Hi, Alex. I got to add you at the last minute from Kara, so that you can. But does anybody in the general audience, not on the committee, have any questions that you'd like to ask? Please go ahead and chime in, or online. I don't know who's on.
Oh yeah. to our for all the people who stay until now, like yeah, feel free to ask any questions. And yeah, if you're able to unmute, if you're not able to unmute yourself, let me know. Send me a message.
All right, let's have one from the audience. Come on, somebody come up with something.
Yeah, Tom, please. Yeah.
Very inspiring. So, correct me if I'm wrong, but
Yeah,
it was an aleatory uncertainty.
right.
So, can you elaborate how these differ from epistemic uncertainty?
Yeah.
In the model itself may
Yeah.
this kind of noise to signal.
Yeah, sure. Yeah, great question, Tol. And I know you've been working on kind of like the combination of aleatoric and epistemic. I believe probably closer to the epistemic. You're not differentiating it that much as I did. So so first again, the definition of aleatoric uncertainty is the data that is inherent in the data where you cannot like correct it if you just have like improved model. What the epistemic uncertainty is that you have like uncertainty inside the model where you hopefully by having more data, then you can kind of explain it away. Where this work is focused on aleatoric uncertainty, and the reason being is that we from the really the probabilistic lens of the model. So we sort of, if allow me to go back quite a few slides, maybe I'll skip that. It's like 60 or 50 slides before, so I'm not gonna click that so many times. But the idea is that again, we start with the framework, which we're trying to maximize the likelihood, the likelihood posterior distribution, and which can be decomposed to the data likelihood term and the prior term. So the data likelihood term naturally kind of fits well with the aleatoric uncertainty framework. And so we just realized that, existing work, if you're using the MSE, then you're essentially assuming a uniform Gaussian distribution, right? So this is where it comes to play. They're not even for the existing work, they're not estimating the aleatoric uncertainty. And we realized that this is not the right assumption. So we sort of like say, yeah, let's take one step further. Can we extend that assumption from homoscedastic uniform to heteroscedastic non-uniform? And that's why we kind of put the focus there. And so for the epistemic uncertainty part, it's another sort of side of the story that we really haven't explored that much, which I believe maybe by adding some dropout layers in the model where you can kind of probe how this, the modus parameter itself can kind of influence the testing distribution. But we believe this is definitely an interesting thing and sort of can be done in a very much complementary way. Yeah.
Anyone else?
Yeah, John, please.
Great work.
Thanks.
So as we work in the medical domain, one of the main challenges, as you highlighted, was our real lack of data.
Mm-hmm. Right.
How does everything fit? There was the trend of, I don't know if it's still how much is going on, synthetic data generation. And is that realistic in the medical domain where pathologies are, by definition, pretty rare?
Right.
We may not account for every unique
right.
human. So
yeah.
Thoughts on that for filling out this lack of data?
Sure. Yeah. This is a great question. So first, let me just diverge that a little bit. So if you're looking at how these generalist models are trained, and if you guys ever attended my Wednesdays on DLRG, then you'll realize that all these models, they're not just purely trained on real world data. They also train a lot on synthetic data. Either it's rendered from some engines or something for some simulations. So it's definitely a plausible path to kind of mix with fake and real data. Let me just call it fake for now. I think for medical imaging, the challenge is it's really, first, I believe this very definitely plausible. I've heard and read some works from the industry, especially in NVIDIA, where they're trying to synthesize some CD images, or even from Siemens. I believe they're doing similar things. So it's definitely a plausible and path. My only take for that is, for medical imaging data, I believe it is harder to generate more realistic images. Why this is the case? If you're thinking about the natural images, right? Like as I said, they're mostly RGB and they're taken by similar cameras, even though the camera parameters are different. But I think the distribution in general in a vision world is sort of closer. In medical imaging, where the image
there are tons of access you have to apply for first.
Oh, so I think in medical imaging, I think the challenge is that it's not the physics behind all these image modalities are very much different, right? And I believe to make it right, like for example, might be a very hard to train a great generalist model that can simultaneously generate CT images, MRI images, PET images, and all that all at once, right? So you probably need to build a specialized generative model for each of the modality. And again, maybe because of the data and all that, it might be harder to acquire such data to do that. But that's one thing. If the end goal is to create super realistic images, it might be harder than in a general vision world. So that's my take one. And the take two is something I believe might be an open direction, is that do we really need realistic looking medical images to help our model improve the performance? And I believe in the vision world, especially for people who work in 3D, where they also have this data scarcity problem, many of the works are arguing that you don't have to make the data look so real but instead, as long as the data carries certain characteristic, it's going to help your generalization. So maybe similar things in medical images, right? As long as you grasp like what is really needed for the images and just focus on that might be an easier fix. Yeah, but that's my general thoughts. Hopefully that answers the question. Yeah.
Thanks.
Okay, if no other questions, we'll move to the committee session. And thanks everybody for coming and hanging in there. Really appreciate it. So
yeah.
Online as well.
Yeah. Thanks everyone online, and thanks for making it so long. And yeah, thank you.
And Larry and Alex. So even if you just stay for a little bit.
Yeah. Thanks everyone. I'll end the Zoom call since it will be a closed committee session. Thanks again. Yeah.
Good. Audible.